Okay, so I'm going to try and explain special relativity as best I can. Sorry if there are some mistakes made because I don't really know how to use Canva. I just wanted a big place to draw. So normally when you draw how objects are moving through time, you put space on the y-axis and time on the x-axis. But in relativity, and it kind of makes more sense because of just the fact that x is on the x-axis. We put x on the x-axis and time on the y-axis. So if you imagine someone standing on a road and then you have a car that's moving, then the car's moving because, just make this a bit more of a straight line, then the car is moving because as a bit of time progresses, it's moved a bit of distance, time progresses, moved a bit of distance, time progresses, moved a bit of distance. And then let's say that there is a traffic light that is, to me on the road, X meters away and keeps that constant distance. Then we want to know, say, because we want to look at how the laws of physics look like to the person in the car, which shouldn't change based on just everyday regular things. When you go inside of a car, you're not in a new universe. So the laws of physics should be the same, but we need to now look at what this traffic light's position through time looks like relative to the car driver. Oh, that's how you drag. Okay. Right. So we can then draw a new graph for the person in the car, which looks like this. And we'll call their time t prime and their space x prime. To them, they are stationary, and the person who was measuring this frame on the road will be moving backwards, and the traffic light that was at a nice constant distance of x will now be moving backwards towards them, maintaining this distance the same, but relative to the x-axis, they're going to be moving with a speed of, let me write this in the color that I used. They're going to be moving where their position through time is going to be the same as the position it was back here, and because this guy was moving with a velocity of v, but now in their point of view they're moving in the opposite direction, that position is going to be minus v times t. And, well, time doesn't change when you're moving fast in this assumption. You know, that's not a thing, that never happens. So that time is the same as that time, and that's the same as that. And these are the transformations for consistency's sake. Okay, never mind. These are the transformations that you end up getting to take you from this guy's point of view on the road to the car's point of view. And that's all well and good. However, in reality, this equation allows for anything at a constant position to be moved by any amount, which causes things like, say, light, for example, which will move very, hold on, let me get a better color for this, which will move very, very quickly to have a reference frame of its own where it's stationary, or have a reference frame where its speed just outright changes, like here. But the speed of light is always constant, as shown by the Michelson Morley experiment. So we need to actually change our way of interpreting what's actually going on here. So let's start again from basics and erase everything else. but we're going to make one little change to our diagrams, which is that the speed of light is really fast, around 299,792,458 meters per second. So if you try drawing that on a graph, you'd end up with light moving. Can I please have my colors back? That'd be very nice of you. Thank you. You'd end up with You'd end up with light moving basically, not even like that, it'd be basically flat, because as 1 unit of time goes by, it's already moved 300 million meters in one direction. So instead, we're going to change our graphs so that we now have speed of light times time on the y-axis, and then space on the x-axis. Now, funnily enough, because speed is distance over time, when you multiply by time, this becomes units of distance, which might sound a bit weird, but sometimes we measure distances with times and times with distances. Like when you say that school is 5 minutes away, you actually mean to say that if you're moving at like a velocity of 20 kilometers per hour, it should take you 5 minutes to get there. So I'm not going to do that maths in my head, but you can use times to measure distances and distances to measure times. But in our case, the constant velocity we're thinking of is the speed of light. And what this means is that in 1 unit of please save this color. Please, pretty please. Yeah. Okay. In 1 unit of time, it moves 1 unit of distance, causing it to move in a diagonal line 45 degrees to the x-axis and the y-axis, which will be very, very important. And this makes the graph CT equals x, or y equals x. Now, if we get rid of this and imagine a train. Okay, we're going to have a train now where there are so this person is on a platform of a train station, and they're watching a train zoom by at looking at the angle roughly half the speed of light. Okay, now relative to the train, or someone standing at one end of the train, and then there's going to be, we'll look at that actually now. Relative to someone, I'm not pasting anything, chill. Relative to someone on the train, where this is the other end of the train, they're stationary, so we'll call this CT prime and X prime, like before. They're stationary. Now let's say that they decide to shoot a beam of light at the other wall, where there is a mirror that bounces it back. Now this might look like a ray diagram, where this is the normal 45, 45, and indeed that is 90 degrees, but we'll see here it's not actually a ray diagram, especially because it's more actually sort of looking at sort of this kind of motion, but when you add a time component to it, it's moving 1 unit of distance, 1 through time like that, then bouncing back. But it's not, this isn't space, it's time. So it's 1 unit of distance, 1 unit of time. So it's the progression of time, not actually a reflection. And when this happens, we can look at the time it took for the light to bounce back. So, I'm terrible at changing colors. So if we mark that here, the time it took for it to reflect, so to hit the other wall and reflect, is the same as half the time it took for the light to come back. So we'll call half the time for the light to come back CTH for CT over half, and the time of reflection as CT of R. So these happen at the same time, they're simultaneous events. And that makes sense, that's normal. But, okay, let's not do that. But, if we go back to the guy on the platform, then to them, when this other person decides to shoot a light beam on the train, the speed of light is constant. So just like how over here the light made 45 degrees, there will also be 45 degrees, that is not 45 degrees, 45 degrees, 45 degrees, making a right angle triangle in a beautiful way, as you can see. Let me actually try my hardest to get a nice 45 degrees. Drawing with the mouse is hard. That's good enough. 45 degrees. Now if we mark the time of reflection versus half the time it took for the light to come back, then we can see that to this guy, these two things don't actually happen at the same time. Whereas to this guy, they do happen at the same time. Now, what can this actually tell us? What does this really mean? Well, if you notice something about these two events, which to this guy is simultaneous, so the light beam reflecting and the moment where it's halfway between the light reflecting, the light coming back, these two events are simultaneous, and because of that, they end up forming a line in between them that is parallel to the x-axis. So all events that are simultaneous, so some event happening here, here, and here, and here, all lie on an x-axis, which means that this is their x-axis. So here, in this case, the line that goes through these 2 points is their x-axis. Sorry, that's not the best line. This line here is their x-axis, and this line up here is their time axis. Yeah. Now we can do a bit of geometry here to look at what the transformation. So remember before we had. Give me a sec. My dad was calling me to eat, so do a bit more before I need to go. So remembering before, the transformation looked something like this. We're looking for essentially this kind of expression now here, but we can use geometry to help us find this out. Also, another fact to know is because the speed of light is constant, then you can say that CT equals x, or CT prime equals x prime, because if we move over here, then here the speed of light moves 1 unit of distance with 1 unit of time, 1 unit of distance with 1 unit of time. So this is going to be very helpful in finding some kind of expression like this. So let's just rub this out, because this isn't necessarily going to be correct. So let's play with some geometry for a bit. So let's zoom in on our little triangle here. Now, something that might not be so obvious is that this length here is the same as this length here, and is the same as this length here. And that's because if you take a rectangle, the best rectangle ever, take its midpoint, go through the diagonals, then all of these will be the same length because that's the midpoint, and that's a right angle triangle. Erase this part, because if I try to erase it, it'll just get rid of the whole thing, and you end up with a right angle triangle where the midpoint of the hypotenuse is equidistant from all the corners. Okay, let me just put that C back. That was an important C. And then if we then just move this line down a little bit, we can put it at the origin and keep it parallel, where we now can have the line over here, and again same length because we just moved the line downwards, it doesn't change anything. And then this length here is the same as this one, because just like how we moved this line down, this line was just moved across, so we end up with a rhombus. And when you have a rhombus, this angle here is the same as this angle here. Now before we do any crazy trig, we can actually just notice something nice about the lines, which is that when you have two lines that are both the same angle from a straight diagonal, then the gradients of them are reciprocals of each other. So that means that this line CT, well, yeah, let's write it in thingy. This line CT prime can be some gradient of CT plus a constant, and then x prime will have that same gradient but times x plus some constant. Because if you think of the graphs, y equals mx plus c and x equals my plus c, not the same speed of light c, then they will have reciprocal gradients because, well, this graph has been reflected in y equals x when you do that, which is exactly what we've done here. Okay, now given this sort of form, we are going to use a better gradient where, similar to how it was velocity times time back there, so let's try looking at x prime to find something similar. Then we know, based on the old throwing random names, well, based on the normal diagram that we made before, so no relativity, just time, space, object moving, where this was t prime, well, yeah, and then it had its own x prime as well, then how x prime was equal to x minus vt. Well, if we then want to have a c there, we'll then have x minus v over c times ct, and then we'll make this guy, because it's velocity over velocity, just some coefficient that we'll call beta. And this is just standard notation, otherwise you could choose any other letter that you want. And then if we try a similar form here, because it makes sense, 1 unit of time, then the 1 year of time, the train moves some distance, so in its point of view everything else is moving some opposite distance with an opposite velocity. It's going to have something that looks like this, but we don't know if the scale of our axes is going to be the same because of the whole speed of light thing. And in maths, it's often best to keep things general and then solve to find more specific solutions. And remembering that the gradient is reciprocal, then you're going to have basically the same form, but we swap the x and ct. And this ends up being our transformation. So let's look for what this gamma guy is. So to find gamma, we'll do ct times ct prime, and then this will be equal to gamma times, oh wait, I forgot to write the inverse transformations, my bad. Well then, to go back, it would just be similar here, where you can then just move the plus vt onto the other side to get an expression for x. You would then end up with x is equal to gamma times x prime plus beta ct, because it's now moving in the opposite direction. And we keep the same factor because due to relativity being relative, then the scaling of the axis shouldn't change. Ct prime shouldn't change because no reference frame is special. Those two are equivalent. And then you end up with a similar thing there. So then using that, we can say that ct is going to be gamma ct prime plus beta x prime times gamma of ct minus beta x. Now we're going to use something very important here that we've kind of neglected, but I said was important earlier, which is that the speed of light is the same in all reference frames. So ct equals x, ct prime equals x prime. We can sub in here, and I'm going to stop doing the fancy colors thing because it's taking too long. And you end up with ct prime. Well, by the way, if this was confusing, this was not a derivative. This is just to make it different without having to introduce a bunch of whole new letters so that we don't have tau's and t's, because they actually mean special things in relativity, so we don't want to throw them in. Move the gamma out, sub in, because x equals ct prime, sorry, x prime equals ct prime, and x equals ct. Then we can factor out ct prime to get 1 plus beta, and then ct to get 1 minus beta. These cancel to give us 1 equals gamma squared times difference of two squares, 1 minus beta squared. Remembering that beta is still, let me actually write that then. Beta is still just your velocity divided by the speed of light, just that ratio. And then this means that from some simple rearranging, gamma equals 1 over the square root of 1 minus beta squared, which is 1 minus the square root of 1 minus v squared over c squared. Woo! Or the Lorentz factor. But this doesn't tell us anything about time dilation or length contraction whatsoever. And also, we actually haven't used the assumption of, oh, nothing can go faster than the speed of light, but you can already see, because of this denominator, that if this is greater than c, this will be greater than 1, this will go negative, imaginary, can't have that. Now, I think I'm going to have to pause to go eat, and then I can come back. But I'm going to keep going, I guess, until I get called. Alright, now to look at what actually happens in these cases, let's try thinking of some time interval. So we have our graph here, back up here, and we want to look at, say, the time interval from here to here. So this time interval. And this time interval is going to be equal to CT1 minus CT2. Alright, time to go. Okay, continuing from where I left off. So we have a time interval every single time. So we have a time interval, T1, T2, and then in this guy's point of view, which I actually forgot to draw all of that back here, but this guy's point of view, you have X and CT, so the guy at the platform. We're now going to look at what that time interval, geez, I'm so cooked, from yesterday, what this time interval looks like in this guy's point of view. So, if we take delta t equals t1 ct1, so actually a delta ct equals ct1 minus ct2. This, by the transformation laws that we made over here, is going to be equal to gamma CT1 prime plus beta x prime minus gamma CT2 prime plus beta x2 prime. Now, because this time interval is occurring at the same x position, because it's just a regular time interval, these are going to end up being the same. So if I can surgically remove that single 2, never mind, that's probably why, then it's going to end up being the same distance, same position. Factor out the gammas, end up with CT prime 1 minus CT prime 2 plus beta x1 minus beta x1. They cancel to give, whoa, chill, to give gamma times CT1 prime minus CT2 prime. So that's delta CT, and then if we cancel the C's, then we end up with that time interval is equal to, if we call this time interval delta t prime, then yeah. So yeah. Now my mom's calling me on my phone. Great. Okay, that's a lot more what's it called? interruptions than I would have liked. But yeah, so an interval in time. Now, the gamma factor is always greater than 1 because the denominator is always going to be less than 1, because if you have velocity, well, less than or equal to 1, because the velocity is either 0 or greater, so then, well, the speed is either 0 or greater, so then you have 1 minus that, and then you're going to have something less than blah blah blah, bigger than 1. So then that means that an interval in time, for me, who's on a platform stationary, is going to, oh my days, I can't even get 1 minute. Right. So that means that a time interval for me on the platform who's stationary is going to be perceived as being a longer time for someone who's on the train. And then that's time dilation. Now, length contraction. Do I have any more colors left? Yes, I do. So let's say we have the length of the train, which we're going to call big L. Now, big L is going to be x1, x2 minus x1. So actually, let's do this instead. How about actually? Yeah, x2, x1. So L equals x2 minus x1. So we can then do a similar thing that we did before, where we use these things that we derived here earlier to get that L equals gamma. Oh, sorry, x2. Now is why it was confusing me. X2 prime, because this is the moving guy's reference frame. So the train's reference frame. So x prime. So sorry, x minus beta ct. So x. I did all of that changing only to end up writing it wrong in the end. Lovely. It's x1 minus x2. So beta x1 minus ct1 minus gamma x2 minus beta ct2. And similar to when we were getting that time interval, these are happening at the same time. We're taking the distances to be at the same time here, so we're not measuring, say, this distance or something. We're measuring this distance at the same time. So then that means that this CT over here is going to be the same CT. So then this is going to factor out the gamma x1 minus x2 minus beta ct1 plus beta ct1. Those disappear and we end up with gamma x1 minus x2. Okay. And we'll call this just the regular length, which is the length that we're measuring of the train. This is the length of the train. It's the length that we're measuring here on the platform. So for us, that would actually look like this length here. sorry. Let me get that correctly. It would look like this length here, whereas to that guy, L would be parallel to their x-axis. And then you end up with, if I can find the equation again, L equals gamma L, or the length that we measure is L over gamma. And that's length contraction, because gamma is always greater than 1, so this guy is always going to be less than this guy, which means that the length of the train is going to appear shorter because this guy's moving in this guy's point of view. And then that's length contraction. And then the simultaneity or simultaneous events thing was how here, for example, the time to reflect and half the time it takes to come back happen at the same time, or the length is measured, the length of the train is measured in terms of the same time. But if you then look here, that's the time taken to reflect and half the time it takes for it to come back no longer happen at the same time. So it's simultaneous for that guy, but not simultaneous for this guy. And these lengths are measured for this guy's same time, but for the moving train, because this isn't a train, this is just a platform. So for the moving train, that length would then actually look like it'd be parallel to that axis and then scaled up, obviously, to hit it. And yeah, so that's length contraction, time dilation, blah blah blah, all explained. There's also other stuff, and like E equals mc squared, but that's complicated. But these are the important equations. So big L, so the length of the train in the train's point of view where it's stationary, divided by the gamma factor, is equal to the length that we measure of the train, where we got the gamma factor somewhere over here, and then the time. Brother, did you not hear me when I said I was recording? Yeah. And then the time interval is just the time interval that this guy measures is the time interval that we measure times thingy. And yeah, that's that. Hope that was helpful. And why is it 37 minutes long?